Hi everyone, what's up? Today I want to show you some examples of how you can use the first fundamental theorem of calculus to compute definite integrals. So today we're going to begin with a pretty simple definite integral. We're going to have the integral from 0 to 3 of the function x squared plus 4x, okay, with respect to x, okay? So now recall that the FTC one says that if you have a definite integral, you can grab the antiderivative of the function in the integrand and evaluate that antiderivative at the bounds, okay? So you're going to subtract the antiderivative evaluated at the upper bound from, no, the other way around, I'm sorry. You're going to subtract, the antiderivative evaluated, you're going to have the antiderivative evaluated at 3 minus the antiderivative evaluated at 0, okay? That's what I want to say, So yeah, now let's do it. So this antiderivative is going to be, so I'm going to write it like this. So this is going to be, by using the power rule, well, we know x squared is going to be x to the third power. And now we need to divide by this same exponent, which is going to be 3, okay? Now, what about this value here? Well, you're going to have 4 times x squared divided by 2, okay? So you're going to get 4 over 2 as a coefficient, which is equal to 2, okay? So I'm going to write plus 2 times x squared, okay? So this is what we get for the second term. Now, you might be new to definite integrals, and I think it's worth mentioning that a notation that is commonly used to represent when you have already antidifferentiated, but you have not computed the definite integral is you write the antiderivative, which is going to be this one. This is the antiderivative of this binomial. And then you write this line, this vertical line, and you write in the bottom, you write 0, and in the top, you write 3, okay? Now, this just says that, well, you're evaluating this antiderivative at 3 and at 0, okay? And of course, you're doing this antiderivative evaluated at 3 minus the function evaluated at 0, okay? So that is what this notation implies. So yeah, let's make that computation. So we're gonna have 3. So we're gonna have 3 evaluated in this function, in this antiderivative, and that is gonna be, I'm gonna write the entire thing, yeah. So this is gonna be 3 to the third power divided by 3 plus, so this is gonna be, we know it's gonna be 9, so that is gonna be 18. 3 squared is 9 times 2, that's 18. So we have 18. That 8 looks so bad. So this is gonna be 18. And now we need to subtract this entire function evaluated at 0. Okay, now this is gonna be pretty easy, but I'm still gonna write it so that we can be explicit in the steps that we followed. So we know this is gonna be 2 times 0 squared. This is 0 squared and close parentheses. Okay, so of course this right-hand term is gonna be 0, so we don't really have to subtract anything. Now this is going to be 9 times 3, which is 27, and 27 divided by 3 is going to be 9, okay? So we have 9, we have here, I'm going to write it here, we have 9 plus 18, okay? And we know this is going to be 20 plus 7, which is going to be 27, okay? Great. So yeah, that's been, this is the result that we have. Now you can see that this is a unitless quantity. I think that's also something worth mentioning. This is a unitless quantity. However, if you're doing physics, for instance, well, this function is going to have some sort of units. So, well, you should, usually when we write the algebra, we don't really focus on writing the units because it's kind of annoying to, write here 3 cubed times, m cubed, meters cubed, or whatever. That is pretty annoying. So usually, we just simply, plug the units at the end, okay? If you're computing an integral, just plug the units at the end, okay? And in this case, well, we have no units, but you could, if you want to, you can write u squared, which is usually, the convention for indicating that you can plug some sort of unit there, okay? So yeah, that's been the entire video. I hope that you enjoyed this problem. It's really nice. It's really easy. It's a good introduction to definite integrals using FTC one, okay? So yeah, that's been the entire thing. See ya.